Okay, so let's go to this spectrum that I had opened up in the last podcast. So just to reaffirm, here is the radiation intensity, which is a measure of energy as well. This is the solar electromagnetic spectrum that we mentioned, goes from gamma rays, X-rays down to ultraviolet. Visible is where we get most of the energy, and near IR and longer IR. And obviously the outgoing infrared radiation net energy going out to space from Earth is in this band way over here away from the visible, okay, centered around 8 to 10. And then we have longer wavelengths like microwave, radio wave, and so on in the solar spectrum as well. Okay, so let's look at the different greenhouse gases here and the total atmosphere. So O2 and O3. Okay, atmosphere is made up of largely nitrogen and oxygen, and yet fortunately they are not greenhouse gases because they are symmetric molecules that allow short wave to go through and that allow long wave to go through as well. But that's in the visible. In UV, O2 is sensitive to UV, so a photon of UV can split the O2 molecule into oxygen atoms, which quickly combines with another O2 molecules to produce ozone in the stratosphere, and then ozone itself also absorbs other UV, essentially giving us mostly an atmosphere that is completely opaque to UV in the troposphere. Good thing, right? Because UV is not good for our DNA, can cause skin cancer and so on. This is why the ozone hole was bad for everybody. We mentioned before ozone hole, Antarctica, whales being affected, phytoplankton production being affected, and so on. And just this year there was also an ozone hole detected in the Arctic, and it's related to CFCs and so on and so forth, and other pollutants that can split ozone, right? So whether life evolved after oxygen evolved to be sensitive to UV, that's not so obvious, because the simplest forms of life go back to 3.85 billion years ago, but they were probably not at the surface. They were deep in the ocean, or well, mostly in some kind of a mud or some kind of a like a what do you want to call it, medium, which was able to allow molecules to synthesize into the first form of life. Oxygen only evolved around 2.4 billion years ago to high concentrations in the atmosphere. The oxygen would have been dissolved in the water, but we have to understand the evolution times of various life forms to understand where UV sensitivity may have come from. Bit of a digression, nonetheless. This shows that the atmosphere in the shortest wave bands is completely absorbing O2 UV by O2 and O3 in the stratosphere, and then oxygen and obviously in the troposphere, oxygen is not a greenhouse gas, but ozone is. So where does ozone come from in the troposphere? It's being naturally produced in the stratosphere, which is a good thing, but in the troposphere it's a greenhouse gas and it's very bad for your lungs. It comes from fossil fuel combustion, coal burning, incomplete burning of petrol and diesel in the cars produces ozone, and so on. Okay, so ozone in the troposphere is bad news for health and for greenhouse gases. Obviously it has these strong absorption of OLR in the Earth's outgoing long wave spectrum. Okay, so focus on this one. CO2 not absorbing in the UV or visible allows solar to come in, and it absorbs in multiple bands. You can see that it has absorption in 2 to 3 microns, 4 microns, and a huge bandwidth of absorption in the 10 to 20 microns. So CO2 absorbs in multiple wavelengths of outgoing long wave radiation. Okay, Earth's outgoing long wave is maximum here, but it emits various other wavelengths as well. Okay, this is what makes CO2 a strong greenhouse gas. Water again allows visible to come in and has many more bands of absorption of near IR and longer wavelengths into microwave and so on. Okay, why is that? Because O2 is very sensitive. Its structure is odd, and I said N2 and O2 allow OLR to go out and sunlight to come in because they are symmetric. CO2 is also symmetric actually, but it has this bending mode sensitivity at these infrared wavelengths. That's what makes it a greenhouse gas. So unlike N2 and O2, which are symmetric and allow both short wave and long wave to pass through, CO2 is sensitive to long wave because of this bending mode. Okay, that's the bad news. So O2 is such a strong greenhouse gas, then is it something to worry about? We'll see later on that actually concentration matters. So O2 concentration can be high in the tropics, and global warming will increase water vapor, as we said. But we'll see a distribution that cold air has very little water. So H2O is what is called a feedback gas. So if you warm it, water vapor will increase. If you cool the atmosphere, water vapor will decrease. And its lifetime is only 8 to 10 days. Average existence in the atmosphere from the time of evaporation, condensation, clouds to rain, it's only about 10 days, whereas CO2, inert gas, can stick around for centuries, which means it can accumulate. We'll see these again. Okay, so here is the total spectrum of greenhouse gases, and you can see we haven't shown methane, N2O, and so on, which are also strong greenhouse gases. CFCs are strong greenhouse gases, and so on. But you can get a good sense of where the greenhouse effect over Earth comes from. So concentration matters, residence time matters, and something called global warming potential also matters, as we will see later on. That's the story, and it's a good story, and you should look at it very carefully, because radiative balance is the crux of global warming. Accounting the energy coming in and energy going out is very critical to understand how much excess energy is being generated by increasing greenhouse gases due to human activities.